Our first presenter is going to be Paul Sutphen from Clear Lake Technology.
Thank you, Bill. Good morning, everybody. It's a pleasure to see you again. I was here back, I guess, last year or the year before, presenting on my Clear Lake Technology presentation. So this morning, I'm here to talk about the phosphorus issue. Phosphorus is one of the things that we at our lakes see a lot of, hear a lot of, and sometimes we're a little mistaken about some of the varieties of phosphorus that are facing us in our lakes. So I was asked to put on a presentation, and Alan Fidelli changed my title, so he put this title in, which is fine. I'm just hoping today, though, that we'll be able to give you some information that you can take back. You've got the whole winter ahead of you to study about it. And I came across this whole thing about organic decay and the cycling of phosphorus. When I did a deep dive back home, I think a couple of years ago, when we had a mysterious issue with a bloom that occurred very early, almost like after the ice went out, we started to have a bloom. It was early April. So I looked into that, and I said, there's got to be some stimulation going on, and found out a little bit about what was going on. The phosphorus is a very reactive element. You'll never find phosphorus by itself. It's always combined with some other mineral or element. And the atomic weight's 15. That means it has 15 protons, has 16 electrons, and they're divided up into 3 spaces around the nucleus of the atom. The organic form of phosphorus is really what we have in our bodies. All living beings and creatures and things like trees and grass and the lakes, algae, are all organically bound with phosphorus. That's what makes the cells in the body move and react and grow. It's a stimulant, and the whole world has phosphorus in the organic form. And what we're trying to do here is to look into the organic side of it, because we don't do that when we are studying the lakes and we're looking at the analysis of a sample taken, and we think about total phosphorus and not other forms. So before I flip the slide, down here are some of the abbreviations that I'll be using. You don't have to really memorize them, they're simple. DOP, dissolved organic phosphorus, and so on here. The 2 big E's are the total phosphorus, soluble reactive phosphorus, and this new thing that I'm calling DOP, dissolved organic phosphorus. Here's a tree diagram, if you could call it that. It shows the total phosphorus at the top. And if you put a filter in your sample, which is 0.45 microns, you will separate the particles from the dissolved part of the sample. And from there, what the lab does is takes the dissolved portion and checks it for whatever dissolved elements you're looking for. In this case, organic is one of them, and soluble inorganic. This is the reactive SRP, and this is the organic. One thing I think is important to know, when you're looking at total phosphorus, it includes the bodies of the algae, the phosphorus of the bodies of the algae, I should say. So if you take a number like 0.03 milligrams total phosphorus, and then you get the reactive phosphorus comes out 0.01, you just calmly say, okay, that means it's very low. But what's the other part that makes up the 0.05 is the question. It's got to be one of these phosphorus listed here. And I found that organic phosphorus is usually what you see that comes along with the inorganic phosphorus. So we started to analyze organic phosphorus at our lake, Culver Lake, when we did our sampling. And it was interesting to follow the organic phosphorus because it has a cycle. So we'll talk about cycle. That's an important word here. We're looking at a cycle that goes from a decay of particles, living particles. They die, and the phosphorus in that gets changed over to a usable phosphorus form. So it goes from organic form over here on the left to inorganic form over here. And how that happens, we'll get into that a little bit. There's the parts of the particulate are consumed by what's called a microbe. It's a mineralization process that consumes the body and transforms the phosphorus in this area over to inorganic phosphorus. So you really don't have a problem with the organic phosphorus in terms of like what we have with the SRP, but I found out that there's a bunch of algae that does like organic phosphorus. The algae that I'm referring to uptake phosphorus in both forms, the organic and the inorganic. The first to come up is really the organic, because if you think of the cycle down in the sediment of the lake, where dead algae fell down during the fall and accumulated on the surface of the sediment, a bunch of little microbes grab it and they start working on it. And it takes about 5 months for the process to complete, from the point in time where they start the process of decay and changing the character of the phosphorus to when it's converted over to SRP. And that's called the mineralization of the algae phosphorus. So, and the way it happens really is, gets into detail. I don't want to get down into the weeds too much, but there's enzymes that are excreted by the microbes that are capable of taking the phosphorus that was bound in an organic form and converting it into inorganic form. It's a miracle of nature when you think about it, because if it laid there on the bottom and it didn't recycle, it would just pile up and be useless. But in real terms, we have cycling happening in our the trees all around us. Anything that has living organisms in it, the leaves drop, they decay on the ground, the nutrients go down into the roots, and they go back up for next year's leaves. Same thing happens with algae. Algae is like a plant. They drop seeds, and when the organisms have broken down the particles, they create a fertilization, which is used by the seeds to grow and release new algae particles. So there we are. It's really happening right now when we're sitting here. The lake looks pretty clear right now because we've dropped out a lot of stuff. Lake is turned over. But what's happening down at the bottom is that we have this action going on between the microbes and the environment at the bottom. And here is the 150 days is roughly 5 months. I mean, it's not exactly, it could be plus or minus months or so. It depends on temperature, really. If the bottom of the sediment is fairly warm compared to other sediments that are colder, that sediment will decay much faster. And I think it's important to know, I'll bring it up in another slide, but the sediment is what's driving, I mean, the temperature is what's driving the oxygen demand or the decay. And all right, so we have some things here, what we need to know about DOP. First of all, it's really seen in the spring from my experience, because during the winter, if you have ice on the lake, you have the decay of the algae going on at the sediment, and it's going to trigger a release of organic phosphorus by the time spring comes. So that's why I have the spring here. We have the DOP, which is suspected to be an important part of our P loading. We didn't know that, but I mean, it really is. And what happens is in the spring, like April, the DOP is available to come up, and when the mixing of the lake goes from top to bottom, you get the DOP coming up around the upper part of the lake where the sun is starting to warm the water. And that's the first thing that stimulates the algae growth. But after that, the SRP, which becomes the major nutrient, increases, and it's the one that drives the algae blooms, really. So the question might rise in your minds, well, how do we deal with it? How do we manage the organic phosphorus? And really, it's not a manageable issue. It's a natural step in the cycling of the decaying process. And the only way you can reduce the DOP is to reduce the algae, period. The quantity of algae that was in the lake last year is what's affecting the lake this year. So you have to have less DOP in the spring in order to reduce the effect of it. It's not there all the time. I have to say that it's a transient condition that happens mostly early in the spring. When I saw this diagram, I was looking at it and I said, oh, this is the water up here, and this is the water, and this is sediment. No. This is a complex diagram, but the brown half is absent of oxygen. The blue is where oxygen is present. This is like a timeline. You start over on the left side where the algae drops down into the sediment. It's still a particulate, and it contains lots of organic phosphorus. And then what happens is the microbes start their processing of this particulate and transfer it into a dissolved organic product, which is down in the bottom of the lake and probably ready to rise up and get into the water column if there's any mixing at all. But the end result of this process that starts over here and ends up here is the phosphate, is the SRP that you have to deal with when you see the algae start to bloom. The SRP is your problem. Now, there's one thing that's being demonstrated here, and that is if you have oxygen, which this upper half displays, you don't get the problem with the SRP because it combines with other minerals, including most likely iron, which comes natural in the bottom of the lake. And it'll precipitate out back to the bottom. So you don't get the nutrients up into the upper part of the water. The next diagram will show you more about how that happens. This shows you sort of a side view of a body of water that on the top has an anoxic hypolemnium and sediment, this whole area here. The thermocline goes along here between the upper warm surface and the cool hypolemnium. And so the sediment is anoxic. It's also anoxic down here where we have oxygen, but the separation is really where there's iron in the sediment that is going to also be released when the sediment gets anoxic. And the iron and the phosphorus come into the solution above the sediment, and they start to follow each other. Then they combine when they get into the oxic zone. When you get oxygen and iron together, you can control your algae and the phosphorus. So oxygen is really the number one thing that you need to get into the bottom of your lake to help solve some of your clarity problems. Of course, it doesn't happen overnight. You have to build some kind of device to get the oxygen down there. At Cobra Lake, we are using a hypolemnic oxygen system, which consists of a 1,200-foot long hose. Let's make it simple. Just a hose that's suspended above the sediment level by about 1.5 feet. And then we put pure oxygen from the oxygen generators that we have on shore into that hose, and they bubble oxygen up into the hypolemnium. And I have to say that they have done some real benefit for us, because we've tracked ORP in our sampling of the water, oxygen and reduction potential. And when it goes negative, then you know you're starting to have a chemical factory develop in the sediment. And that's going to release the iron, it's going to release the phosphorus, and that's all going to be a problem for you, because it'll be in the upper waters when the lake mixes in the early fall. So this oxygen system that we have put in keeps a level of oxygen available. We're not talking about habitat high oxygen, but it's enough to keep the sediment in a positive ORP, and I believe that has helped really reduce the internal circulation of phosphorus into the lake. We call it the internal loading of the phosphorus. Yes, sir.
Just a quick question. I'm wondering how deep your lake is, and is the depth of the water a factor here?
Yes, it is. Our lake is about 50 feet up nominally, and it gets down to zero oxygen by July if you didn't have any help, because I wanted to show you in another slide that if you size your oxygen system for the sediment temperature that is in the wintertime, and then by summer it's going up, let's say by 10 degrees higher, which it normally is about 10 degrees higher, the demand doubles. So if you size your oxygen system for whatever, 1,000 kilograms per day of oxygen, per day demand, then it'll be 2,000 kilograms oxygen demand per day in the summer. So then you lose your oxygen a lot faster. It just goes right down. And it would be nice if you could throw some ice cubes in the bottom of the lake. But coming up with solutions to give this deep water lakes oxygen when they need it is a real challenge. There are some scientific ideas out there that will provide that, a little bit of relief in that, but it costs money to run pumps and oxygen oxygen machines. Actually, they make 95% pure oxygen, so you're only going to get 20% of the air volume that you put through 80% is going to be nitrogen or other gas. Yes, ma'am.
Are you referring to an OST system or aeration?
This is a different type of aeration. It aerates, but it does it by not bubbling air. It's bubbling pure oxygen, releasing it and letting it come up, and then it aerates the waters. But anyway, that's okay. Here's some of the things that you can kind of figure out from the presentation so far. We have to look at total phosphorus really by asking a secondary question: what is it made of? It's not just particulate; it's other soluble or dissolved components. And DOP and SRP probably, if you add them together, would equal very close to TP. But if you don't do analysis to get the DOP, you'll see a little bit of a gap between subtracting the SRP from the TP. So in other words, it's sort of just a breakdown of what the TP really is. TP is considered the major parameter that you look at when you say, what's your TP in your lake, and you get the answer and you just kind of can tell whether that lake is really eutrophic or not. But it's important to see what the aggregation is that makes up the TP. You have to watch out. If you have an early stimulation of the algae that's starting to grow in this early spring, it's probably due to the organic, because that's the first that would appear. And how to minimize, I said before, the best way is to mind getting your phosphorus level down to begin with. Looking at your watershed and minimizing the internal phosphorus load, but the watershed is the big load that is always running into the lake when it rains, and septic systems are always flushing toilets and so forth. And until you can get that way down, you'll get relief from the algae, and your clarity will go up, and this DOP will be very, very minimal, because everything kind of goes down when you get the oxygen under control, when you get the phosphorus under control. Winter ice is a problem. When your lake freezes over, it actually seals off the lake from any external oxygen. And it will go anoxic much quicker with ice cover. We found that out last year. We had a good ice cover for a change. For many years we haven't had an ice cover. How many of you had a full ice cover? Yeah, see, that's good. I mean, it's good in a way for fishing or for recreation, but it's not good for the oxygen level in the lake. It's going to go down pretty quickly. When the ice starts to break up, it's about the time when you get, about a week or two later, you get that big wind coming in, it breaks the ice, the waves are running around, and the lake mixes, and now you got all of this SRP up in the whole body of the water. There's no thermocline, so it's going from the bottom right up to the surface. And it's a rather risky time in terms of what the algae is going to do, because it's looking for nutrients, it's looking for sunlight, it's going to be up at the top, and watch out for the beginning of some algae problems. So anyway, this is pretty much what I wanted to get across, and I'm open to any questions. We have a couple of minutes, right, Alan?
Right, yeah.
Yes, in the blue shirt here. Yes.
Yeah, you said your lake is 50 feet, and you're using oxygen to bring oxygen back into that area. What level of the lake is not effect to use oxygen? In other words, if it's 3 feet deep your lake, would that be in 1 foot above with your oxygen network? What level does that, is it effective or not?
Well, it dissipates as it goes up because we didn't want to mix the thermocline. We wanted to keep the thermocline, so we're not trying to de-thermocline it.
But I'm just saying, what level, like, in other words, would you recommend this for a lake that's 40 feet deep, or 30 feet deep, or 3 foot deep?
Yeah, the thermocline sits at about 6 meters, and the bottom of the lake is around 13.5 meters.
So what, 3.5 meters, you said?
6 meters for the thermocline elevation, and the bottom is around 13.5.
So 3, so it's 18 feet?
Yeah, but we're not getting a lot of oxygen way up high. It's mostly down below.
So if
So what if
As
your lake,
the
what if your
bubbles
lake,
go up, they get smaller and
I
smaller.
understand. So if your lake is 18 feet deep, is it effective to use an oxygen system, an aeration system?
Well, an aeration system, it depends on what kind of airlift systems. We used to have one of theirs for 30 years in the lake. Excuse me, I got. Oh my gosh. My great grandson came to the house on Tuesday or last weekend, and I kissed him goodbye, and I noticed he had a cold. Well, guess what? Here I am.
And then another question for you is talk about removing the algae from the year before. Would you do that with weed harvesting too?
Weed harvesting, well, weed harvesting takes nutrients out of the water. If you throw the weeds away, just get rid of them. Not a lot of phosphorus. But weeds have an ability to absorb phosphorus, so there's a careful balance that you have to make. And we only spot treat with herbicide, and we leave some weeds in the lake, to take care of fishermen and also keep the phosphorus there.
Maybe I'm just using a weed harvesting tool to pick up the algae bloom from 1 year. Would that help reduce the algae the next year?
Oh, I see what you're saying. Well, you have a shallow lake. You must have a shallow lake, because the harvester can only go down about 6 feet. The weed harvester can only reach down about 6 feet, because it goes on the surface and then it can drop its cutters down about 6 feet.
I understand. So the question is if you harvest the algae, you have an algae bloom, and you harvest it the 1 year, will that reduce the algae next year?
Yeah, I don't think the harvester's going to improve your algae problem. It'll make it worse, if anything. Yes, sir, behind.
Some of us have a lake that was dammed up in the Rockaway River, so there's constant flow coming underneath. So
Right.
Is that mixing stuff up constantly, or does it dissipate the longer your lake is?
Well, it probably flushes a lot, so you're replacing water that has phosphorus in it, and it can reduce your phosphorus loading, I would think. But in terms of affecting the bottom of the sediment, it sits there. Every lake has sediment laying in for years and years. I mean, once phosphorus goes in the lake, it stays there forever. A little bit will carry over the dam, but every bit of phosphorus that you take into your lake, pretty much all of it stays in the lake.
Yeah, plus we have a golf course upstream too, so that doesn't help things either.
Right. We're fighting a tough battle, folks. I'll tell you that with phosphorus and keep getting these lakes turned around, because so many years we've had all this phosphorus go in, and man has settled into these lakes, and when man came, it changed the ecology of the lake and what's happening to the water. So to reverse all that takes a lot of time, money, effort, technology. Back in the
Have you explored or done any research toward adding any biological or probiotic things in some of your
your question was to add any kind of chemical, you mean?
No, biologicals, like
Like bacteria eating organic?
to
I don't know a lot about that, ma'am. I'm a little skeptical. Because we have natural organisms that are eating up the organic material all the time. And you put in the wrong kind of bacteria, and maybe you're going to have a problem. Maybe it'll make more of a problem. Yes, sir.
Do you know offhand, for your system, what your capital investment and then operating costs were to generate the oxygen?
I don't have the numbers, I'm not on the board, but it's a little more expensive than we had with the other system that was an airlift system. I don't want to get into too much detail about the operation of it, but it is more costly. It has the same compressor capacity. They sized it with 140 and 130 horsepower compressor. The two oxygen generators can put out about 10 CFM. And you ask yourself, well, what happened to the 100 CFM we had from the compressor? Well, it all gets vented as nitrogen. Because remember, the oxygen's only a small, like 1/5 of the, yeah. Yes, sir. Ma'am.
My other question is, when you're tracking the different types of phosphorus, when you talk about the DOP, is that a lab test that's being done? And if so, what lab are you using? Because different labs do different types of phosphorus analysis.
Yeah, thank you for the question. The lab that Princeton Hydro uses is ECM. We used to use other labs, but I've seen different results from different labs in terms of the number of significant figures they go in reporting. I mean, usually when they report, when I did the testing of the septic systems in Culver Lake, we were using, started out using integrated labs down in Rockaway. And then they shut down. We moved over to, I forget the name of the lab, but it's down in near Clifton. You would recognize the name. And they changed the nomenclature, or the numbers, significant numbers of the reporting quantities. And I was used to looking at milligrams of like 153 for 0.153, like 3 significant figures. The laboratory that we're having from Princeton Hydro gives you 2 significant figures, 0.01 or 0.02 or 0.03. And anything in between, you have to guess. It's not there. Does that answer your question?
It does, and I know that you didn't mention the other one was pre-reactive phosphorus. I know that the CPRO lab does pre-reactive instead of soluble.
Yeah, the measurement of reactive is not as difficult, but the DOP is calculated by subtracting the SRP from your total dissolved phosphorus. And that's
Say that again, the DRP is calculated by subtracting the SRP from your total.
From the total dissolved, TDP. That would be both the organic and the inorganic together. And if you measure that total, which you can easily, then they measure what the SRP is, which is easy to do. And the left, they subtract that number from the TP, the total. And that's how you get the what's remaining, which would be the organic. Probably costs a little more money to do that, I don't know. One more question maybe, Alan? Yes, sir?
Well, how long do you have to have ice over to be concerned? Because like our lake, we had short period, maybe 3 weeks at the most, and then it got warm, it melted. I think we had a short ice over a few weeks later.
Well,
are we talking months worth of ice over, or?
Well, just a partial ice over is not a problem because the lake is open to the north.
but it was only for a short period of time.
Yeah. If you have a whole winter, like 3 months of ice, then your lake is pretty much gone for oxygen.
Right.
Even though it's at the colder sediment temperature where it's a lower level of oxygen demand, it's still every day those bugs are in there doing their job.
Most of us haven't had a winter like that in 7 or 8
Yeah.
years now.
Yeah. And we don't want to run the oxygen system underneath the ice either. That's a safety problem. One more question here? Okay, thank you very much.